And now you have what's new about the so-called river. I made the sketch last time, but this time I'll make it much better. I'll assume that the river has a rectangular cross-section. Here's the cross-section. The river has a grade called alpha. And unlike in the previous lecture, the flow is not driven by a pressure difference. It is driven by gravity. I show that by the way, this prism is a volume filled with fluid. In the gravitational field, that body of water has weight. The weight of this particular, let's call it, it's not a beam that's solid, but anyway, this prism is the volume, which is, if that's cross-sectional A, if the length of the channel is L, then the mass is the density of water, A, L, and then G. This is the weight. And what drives this, let's call it slug of water downhill, is the component of this weight aligned with the channel. And so the one that does not move the water is perpendicular. The one that moves the water, and Adrian forgot his colored choke again. Don't report me to the authorities, but that's what happened. Anyway, so that component is alpha times the weight. Why alpha? Because it should be sine of alpha is essentially alpha, because alpha is a lot less than 1 when expressed in radians. Get it? We're helping ourselves big time at every step. We don't deal with trigonometric fractions. We're just be happy with algebra the old-fashioned way. Alpha. And then comes the question of, well, the flow is from left to right. How come the thing is moving without a pressure difference? Obviously, this component of the weight is doing the pushing. And so the next move is to find what is delta P here. I mean, in this new problem, what force really plays the role of force that does the pushing. And we do a force balance on the sliding body of water. The weight, which is rho A LG, then multiplied by this angle alpha, is being balanced by all the shear stresses integrated over the wetted surface. That's tau, and then P is the wetted perimeter. By the way, the wetted perimeter in this particular drawing looks like one of these staples, a rectangle with a missing top. So tau times P times L. Previously, meaning in the previous lecture, on the left-hand side was delta P times A, balanced by the same friction force integrated over the wetted surfaces. And that means that the previous lecture, which was lecture number 5, not number 4, what was called as delta P is today the group rho A L G alpha. Said another way, that the delta P of the previous lecture is today the group rho L G alpha. Small grade, small driving force. Always ask your body senses whether what you just wrote makes sense, whether it matches your feelings. That's what sense really means. Okay. So that's the first aha. So therefore, we use the mathematics from one lecture ago, mathematics that were written over here like this, delta P. Now that we know what delta P really is today, that's today. So delta P times A equals all of this P L tau. For tau, we we replace tau with the definition of skin friction coefficient, which is that dimensionless, here is dimensionless, F times a factor that has the units of pressure, where capital U is the average velocity of the fluid through the cross-section. In other words, all of this squared is substituted in place of U squared. In fact, I'll do it right now. M dot squared over rho A squared. And this takes me to the to an expression that looks like an expression for the flow resistance through a river channel, which is the across variable delta P divided by mass flow rate squared. This is new. One lecture ago, this kind of grouping on the left-hand side had the mass flow rate through the tube to power 1. It looked like voltage divided by current. And not so in the case of flow through a river channel, because as I'll show you next, this F is in fact a constant. It doesn't depend, essentially a constant, doesn't depend much on the speed of the flow. So the expression for what really matters, because you want, you're pursuing, I call it access or ease of flowing, another word for my feeling the presence of freedom as opposed to obstacle. The so-called resistance is between the across and the through squared in this case. But of course, qualitatively, or when it comes to feelings, is the same idea that the way you push manifests itself in the form of a flow or a current or movement, let's call it. Anyway, so you get this expression F L over 2 times the density of water and then the wetted perimeter over the cross-section cubed. Okay? Several observations follow. First, I already mentioned the fact that the friction factor is fortunately a simple kind of mystery, easy to figure out. Most of you are taught the Moody chart, which is a log-log representation of friction factors versus Reynolds numbers based on hydraulic diameter in all sorts of duct cross-section configurations. You've heard of the Moody chart? No. Then you're lucky that you hear those who have not heard, are lucky to hear about it for the first time from Adrian. The Moody chart is actually came from Prandtl and his student Nikoradze. They published it in the early 1930s. Shortly after that, meaning Nikoradze was doing his PhD thesis. Nikoradze was this is now Germany, lucky enough to escape from Bolshevism from Georgia, the same so-called republic of the USSR from which Stalin came. Anyway, so he was the student of Prandtl. And Prandtl wrote the first edition of his very, very famous textbook on fluid mechanics 1 or 2 years after the student, and made this graph famous. But Moody, during the war, meaning a little more than 10 years later, published, this is an American, published in the ASME Transactions an expanded, much more detailed, on a finer log-log grid that opened on several pages. Back then, slide rule, the graphic display of information was aided by talented graphic artists such as Moody, so that the engineers could pick numbers or values by reading this fine grid with finer details, you see. Anyway, from your distance, the so-called Moody chart shows two things. First of all, to the left of something like a Reynolds number of 2000 is F for laminar flows. To the right, higher Reynolds number, turbulent flow. In the laminar realm, the relationship between F and the Reynolds number, and you know it from this formula from Poiseuille, that F equals some constant of order 10 divided by the Reynolds number based on hydraulic diameter. Obviously, a line with slope of -1 is what you see plotted, except that there is one such line for every cross-section, a lower line for the round tube, a higher line for the slit. So there is a family of these straight lines. Of course, you don't need Moody for that. You have these formulas that I put on the blackboard last time. On the right-hand side of this so-called transition Reynolds number, you have another bundle of curves, and this is where Nikoradze made himself and the professor and the laboratory famous. Nikoradze, of course, measured the delta P and the mass flow rate squared, but he did it in a multitude of channels, pipes in his case, round pipes, with controlled internal surface roughness. He used sand with different size for the granules, and mix that sand with clay, a particular kind of glue, and then dipped his tubes in this stuff, and therefore coated the inside of the tube with roughness from fine to very rough, and obtained a family of curves that look like this. The more rough, the higher the curve. And what is most useful about this work is the thing that at high enough Reynolds number, roughness is the news of the day, meaning that the friction factor depends on roughness, not on Reynolds number. So, the bottom of the river is rough. In the mountains, the bottom is basically full of boulders. That's a large-scale roughness. We can get into why the protuberance from the bottom has the effect of friction on the column of water that rubs against that bottom. We can get into that if you're curious. But you get the feeling, in fact, that you agree with the fact that flow through something that's rough is resistive. And when very rough, as in the case of river bottom, this constant is of the order of 100. Okay? Get it? By the way, this is a high value on a chart because obviously you can draw these lines down, if you don't know fluid mechanics, down to very small f's, even for laminar flow, even though laminar flow does not exist at higher and higher Reynolds numbers. All right, so the good news for us is that this f is a constant. Not really. It is a constant because we're not on Earth to waste our time, okay? We're here to figure out why wide rivers are deep. Meaning, can we predict that why the river should be deep? That is the let's call it what's the word? It's like the carrot in front of the horse, you know. The bait. That is the bait, okay? We fall for it. And, well, let's find out. First of all, we see here that the shape of the channel cross-section is influenced at the most by this group, P over cross-section to power 3. But once again, because I'm not on Earth to waste my time, the cross-sectional shape of a river speaks of the age of the river. The river was born, actually it was born much earlier than the mountains, meaning a very long time ago. This is why the bottom of the river in the mountains is rocky. In other words, A has to do with the age of the river. And that means that to us mortals in this particular problem-solving exercise, capital A is fixed. It has to do with age. Incidentally, do you know why the river is older than the mountain? The mountain happens because the Earth's crust is rising, always rising. We talked about Mount Everest, the Himalaya. It's rising as we speak, you know, because of the collision of the Indian subcontinent against the Asian landmass. They collided, of course, a long, long time ago, but they really collided. And that place of collision is rising. Well, the river does its thing. The river is sowing like a chainsaw through the surface that, from the point of view of the river, is getting in the way, that rising surface. So every time you see a canyon, for example, the Grand Canyon, or all these mountain passes all over the world, these canyons, they are not cut through the mountain by the river yesterday. Yesterday, the river that would be formed by a sudden downpour would flow around the mountain, not through, not over the mountain in, chainsaw fashion. So the reason the geophysical map of the globe looks the way it does today is that rainfall is older than the mountain. Get it? A little bit counterintuitive, but that's the only explanation. It has to do with which came first. And that means that if you are contemplating easier and easier access, it has to do with the fact that maybe the answer comes from smaller wetted perimeter at fixed A. And why not think about this with respect to this first drawing, which looks like the unused staple. So in cross sections, and we're talking about a rectangular, an assumed rectangular cross section. There are such cross sections today. They are made by people in these levees, famous or infamous around New Orleans before Katrina, and other artificial channels in laboratories of civil engineering. There's one such thing downstairs in this building. Yeah, people make them a rectangular cross-section, meaning they are artificial, not natural. But we say, gee, what if the cross-section is rectangular? So this is the solid substrate. Here is the so-called free surface. What distinguishes the river channel from the duct of last lecture is that one side of the cross-section is stress-free, meaning the flow does not rub against anything over the top. So that's free surface. It is high on the river that the water velocity is the greatest. And the wetted perimeter, never mind that. First of all, the width is W. The depth is D. And the cross-sectional area, which is fixed, is WD. I would not write it DW because then you think I'm throwing calculus at you, so I'm not doing that. I like calculus, but I think I don't like jargon, okay? So, and then the wetted perimeter is 1W plus twice D. That's the wetted perimeter. I'm interested in smaller. And the degree of smallness is free to vary because my drawing is any such drawing, except that W and D are not independent, meaning they are not 2 degrees of freedom, they're only 1. Because of the fixed cross-section, which is the product of the 2. Said another way, instead of D, I write A over W. So the single degree of freedom is W. Now, speaking of technique, you should be jumping up and down in your shoes that you have encountered again the ultra-friendly competition between Roman 1 and Roman 2. Here is the degree of freedom. On the ordinate, I write P. And you see here, Roman 1 is a straight line. Roman 2 is a equilateral hyperbola. You see already the existence of a trade-off between the two, meaning a width that satisfies, how should I say, balances the two asymptotes. In this case, the minimum wetted perimeter corresponds to the width that is found by intersecting the asymptotes, meaning setting Roman 1 and Roman 2 equal in this case. And that means what? The W equals twice, and then A over W. A, however, is the product of W and D. And from this, the conclusion that for easier flowing, so the first answer is that for rectangular cross-section, the ratio of W over D should be 2.